1. Application of databases. Databases are crucial in everyday applications like web shops, CRM systems, and financial systems, referred to as line of business (LOB) applications. Choosing between a SQL database and a Cosmos DB database is important for optimal performance and scalability. 2. Importance of data. Data has become increasingly significant in recent years. Nearly all applications, from CRM systems to social media apps, rely on databases to store data. 3. Types of databases. Historically, relational databases have been dominant since the 1980s. With the rise of big data, NoSQL databases have emerged. NoSQL stands for Not Only SQL, indicating alternatives to traditional relational databases. SQL, Structured Query Language, is the programming language used in relational databases. 4. Chapter Learning Objectives. Basics of databases, focusing primarily on relational databases, but applicable to other systems. Topics include Overview of relational databases, Introduction to SQL, Impact of intended usage patterns on database design, Understanding relational theory, Keys, Types of workload. 5. Historical context. Before databases, data was stored in files, such as comma-separated value, CSV, files. Example of a CSV file shown as %CSV, with data but lacking additional context or metadata. 6. Challenges with flat files. Flat files, like CSV files, present issues. Lack of clarity about the type of data, e.g., whether individuals are patients, customers, employees, etc. Insufficient information or context within the file itself. Here are the key points from the text. Drawbacks of using flat files to store data. 1. Lack of data context. Inability to infer data meaning. Flat files do not provide clear context or metadata, making it difficult to understand what the data represents. For example, without column names, it's hard to determine what each value, e.g., postal code, salary, signifies. Absence of metadata. Metadata, data about the data, is not stored with the actual data in flat files. This includes column names and data types, e.g., numerical, alphanumerical. Metadata helps in understanding and processing the data correctly. 2. Programming and performance limitations. Lack of flexibility. Flat files require custom code to process data, which becomes inefficient with large files. For instance, searching for a specific value involves reading through each line, which is slow for extensive datasets. Breaking code with structural changes. Changes in file structure, e.g., adding columns, can break existing code that assumes a fixed format, leading to errors and inefficiencies. 3. Concurrent access issues. Single user limitation. Flat files are not designed for simultaneous multi-user access. In scenarios where multiple users or processes need to interact with the data concurrently, flat files are inadequate and prone to consistency issues. Need for databases. Relational databases address these issues with features like ACID properties, atomicity, consistency, isolation, durability, that ensure reliable multi-user access and consistency. 4. Historical context and evolution. Initial workarounds. Early solutions like ISAM and VSAM files attempted to address some limitations of flat files, but had their own constraints. Introduction of database management systems. DBMSs. The challenges associated with flat files led to the development and adoption of database management systems, which offer more robust solutions for data storage, processing, and multi-user access. Modern alternatives. XML and JSON files. Modern file formats like XML and JSON store metadata along with data, making it easier to understand and process the information. The affordability of storage and computational power has made these formats viable for storing data and metadata together. Key points breakdown. Introduction to databases. 1. A database is a self-describing collection of related data aimed at providing information to people and applications. Early database history. 2. The first databases appeared in the 1960s as hierarchical databases. 3. Network databases followed but lacked flexibility for complex organizations and multiple users. YEF-COD and relational databases. 4. In the early 1970s, YEF-COD, an IBM mathematician, developed the theory of relational databases based on mathematical set theory. 5. COD's theory described large sets of elements with simple rules, applicable to real-life collections such as customer data. Relational databases explained. 6. Relational databases store data in tables, deriving the term relational from the relationships formed between tables. 7. Example: two sets of data, such as numbers 1, 2, 3, 4, and names Peter, Janek, Yari, Mats, can be combined into a table, forming relationships between the sets, e.g., 1 and Peter. Table structure and metadata. 8. Columns in tables have specific data types, such as int for whole numbers and varchar, 50, for text up to 50 characters. 9. Metadata, including data types, is part of the table structure, combining data and metadata in a single entity. Relational database structure. 10. Relational databases typically consist of multiple related tables. 11. The term relational refers to data storage in tables, not merely the relationships between tables. Relational Database Management System, RDBMS. 1. An RDBMS is software for creating and managing databases according to COD's theory. 2. RDBMS functionalities include creating tables and storing data in them. 3. Provides management services like data security for authorized access. 4. Allows data creation, storage, management, and accessibility. 5. Examples include Microsoft SQL Server, Oracle, IBM DB2, MySQL, and MariaDB. Definition and note. 6. An RDBMS adheres to COD's relational model rules, enabling comprehensive data management. CSV file problems and RDBMS solutions. 7. CSV files lack metadata, whereas relational databases include it. 8. Relational databases offer flexibility and performance beyond CSV files. 9. Introduction of SQL is necessary to understand relational database operations. Structured Query Language, SQL. 10. SQL is the standard language for all relational databases. 11. SQL is used for reading and manipulating database data. 12. Database creation, table creation, and data security are managed using SQL. 13. Tools can generate SQL code for database developers. SQL categories. 14. SQL consists of three main categories: DCL, DDL, and DML. Data Control Language, DCL. 15. DCL secures data with three statements: grant, deny, and revoke. 16. DCL is outside the scope of the book, with further information available online. Data Definition Language, DDL. 17. DDL statements create and manage database objects with three statements: create, alter, and drop. 18. Create table creates a new table. 19. Alter table modifies an existing table structure. 20. Drop table deletes a table and its contents. Data Manipulation Language, DML. 21. DML works with the actual data in tables with four statements: select, insert, update, and delete. 22. Select reads data from tables, sometimes considered a separate category, DQL. 23. Insert adds new rows to a table. 24. Update modifies existing row values. 25. Delete removes rows from a table. Note on SQL and NoSQL. 26. The book is not a comprehensive SQL tutorial, but resources are recommended for learning T-SQL, SQL Server dialect. 27. SQL is fundamental for both SQL and NoSQL databases and essential for data professionals. Understanding database schema. 1. Creating a table. Use create table to create a table. Specify the table name, column names, and their data types. This process defines the metadata. 2. Database schema. All combined metadata is referred to as the database schema. Schema often refers to table structure and relationships. In SQL Server, a schema is also an object aiding security strategy. 3. Note: schema of a database includes all tables and their relationships. Inserting data. 4. Loading data. Use the insert statement to load data into the table. Enter values for all columns, adhering to the defined data types and constraints. 5. Working with data. Use the select statement to read data from the database. Example query. SQL. Select postal code. From persons, where name equals Janek. The database uses metadata to optimize query performance and retrieve data flexibly. 6. Set-based operations. Relational databases operate on sets of rows, not individual rows. The where clause determines the set size: one row, multiple rows, or no rows. 7. Optimization and indexes. The database engine uses metadata and structures like indexes to optimize queries. Chapter 4 will cover indexes in detail. Advantages over flat files. 8. Flexibility and optimization. Tables offer more flexibility compared to flat files. No need for repetitive steps for each row. Database engines optimize for fast query response times. Use cases and impact on design. 9. Database design. Different use cases affect database design. Understanding use cases helps in designing efficient databases. Note: 10. Query performance. Database systems utilize schema metadata to optimize queries, ensuring good performance even with large datasets. Impact of intended usage patterns on database design. 1. Simple versus complex databases. Simple databases may consist of just one table. Most databases have multiple tables, up to tens of thousands. 2. Data modeling. Deciding which tables and relationships to create is crucial. Data modeling is the process of determining the table structure and schema. 3. Note: data modeling involves deciding on the data structures for storage. 4. Normalization. Concept introduced by Jeff Cott. Involves following formal steps to achieve an optimal schema. Databases often aim for the third normal form. Chapter 3 will cover normalizing data. 5. Alternative modeling techniques. Chapter 7 covers dimensional modeling. Chapter 9 covers data vault modeling. Different techniques lead to different schemas impacting query performance and cost. 6. Use case examples. Webshop databases benefit from normalization for quick data retrieval. Data warehouses benefit from dimensional modeling for handling large datasets. 7. NoSQL databases. Chapter 5 covers NoSQL databases and their rules. 8. Commonality in modeling. Regardless of the database type, modeling similarities are greater than differences. All databases are collections of data describable by set theory. Understanding relational theory. 1. Relational databases. Store data in tables based on Codd's relational model rules. 2. Pillars of relational theory. Pillar 1. Elements of a set are not ordered. Pillar 2. All elements in a set are unique. 3. Order of elements. Databases do not store rows in a specific order. Flexibility and write performance are benefits of unordered storage.